Professore, non sentiamo.
Ok.
Sì, adesso
Quindi
sì,
stavo
grazie.
dicendo, ok, scusate. So we'll go back to where we were at yesterday. So the subject of the lecture will be, again, the misrepresentation which are connected to the representation of rigid body motion. So energetic misrepresentation of rigid body motion, or rigid motion. We were in particularly ascertaining the case of the 2D isoparametric rectangular element. And in particular, we can already use, it should be this one. Yeah. So here, what we did was basically deriving the values of the various nodal coordinates expressed in the inertial frame. And what we were able to derive eventually was the following structure. So we had the position of each point within the element could be expressed as the element shape function applied over the element, the nodal coordinates. And this we found out to be equal to R1 plus x10 over bar cosine of theta minus x20 sinus of theta. And the second component, of course, here we are in the two-dimensional case, so we have two components of theta plus x20 cosine of theta. Now, again, this one here we had already derived yesterday, so it's typical for each element. So once you have determined for the element, it doesn't matter what kind of motion you are describing, so we know it already. And this, instead, we derived it yesterday, so we just applied this matrix multiplication to two known quantities, and this is the result. Now, the idea is to associate to this position field of each point within the element, again described with respect to the inertial frame, a potential a strain energy. Okay, so we define a strain energy U, which we can define as the integral over the area. Well, in fact, just to be super correct, it's the integral over the volume of our element of what? Of the stress vector transposed applied over the strain vector integrated over the volume. In this case here we are using what is called volt notation. Okay, you know it when you use, basically when you represent stress and strain as a column of 6 components. That's called volt notation. Because otherwise here we should have a tensor notation. Okay. But let's keep it simple. So this can be written as the integral over the area of what? Of the strain vector transposed applied over the elastic matrix, which we can call C, transposed, applied over the strain vector, and then we apply it, we multiply it actually, and also pre-multiply it, the thickness of our body and the area. Okay, so this is the, for example, for our case, in case of a linear elastic constitutive law, this is Hooke's matrix. In theory, it should be a tensor. Okay. But again, if we use Voigt notation, it's not anymore a tensor because it does not fulfill anymore the geometrical properties of a tensor. It's a matrix. Okay. So keep in mind the difference between tensor and matrices. Matrices are, let's say, like vectors are a container of elements with no geometrical properties. Tensors are physical quantities. They are mathematical entities which represent physical quantities and do possess particular properties when it comes down to transformation with respect to reference frames. So it's another thing. Even if they can look the same, they are different. So this can be Hooke's matrix. And as you can see here, we have the typical quadratic form, epsilon, pre-multiplying and post-multiplying. So this is the strain energy. And we can define the deformation as such. We can define the deformation again. This part is largely resound in chapter number 3 that we didn't deal with during the course, but again, it's there for you if you want to have some additional information. This should be, let me just check. Okay, so can I actually crop this? I think I should be able to crop this, no? Not sure. Well, whatever. Let's keep it like this. We define it as, so again, do not mistake these I, J indices. These are subscripts, and these are the direction of derivations. They have nothing to do with body numbers or element numbers. Okay, so this is true even outside multi-body space structure. Okay, just the direction of derivation. Well, if we use again the linear definition, this can be written as okay. So again, this is linear elasticity. Actually, small deformation. So this is the small deformation hypothesis when I put here, because you know that here I would also have a nonlinear term in the deformation typically that we missed. So this is the linear Green-Lagrange deformation tensor. So we are in the hypothesis of small deformation that we have retained since the beginning. So we stay constant with this. And please be aware of this because this is going to be important also in the following. what is this? Okay, what are these W here over bar? W over bar, and that's why I introduced this picture, are basically the displacements induced by the deformation on the element described with respect to the local frame of the element. If you want, they are the elemental counterpart of what we have called U over bar. Okay, so U over bar were the displacement induced by the deformation in the body, described with respect to the local frame of the body. So here, W over bar are the displacement induced by deformation expressed on the element, expressed with respect to the element to the reference frame of the element. Okay, so here. So you see, we have P0. After the deformation, it goes to P, and so it basically undergoes a displacement W over bar. Okay, so, and this is the deformation. Okay, which is the typical definition. All right, so we have the energy, strain energy here, which is just expressed in terms of deformation, okay, and elastic constants, but this we assume that the material is known of the body. So what we have to do is to calculate first this W, okay, so this displacement induced by deformation. All right, we had, if you remember, so for a single body, we have the following. That the position of a point described with respect to the inertial frame, and this is the typical writing, is what? The position of the origin of the local frame plus the position of a point described with respect to the local frame. And again, we elaborated on this, and what we got was that this could be written as such. So the local position expressed with respect to the local frame. And again, to further let's say, develop this expression, we have that the local position could be expressed with respect to the initial contribution plus what I was, again, writing before. So the deformation induced by the displacement induced by the deformation on the body expressed with respect to the local frame of the body. Now, you can think of our case in which we have this element here as a body composed of a single element. Okay, you can do this parallelism if you want. In this parallelism, so single element parallelism, we have that basically our frame B1, B2 becomes what? I1, I2. Okay, for the local frame. Then we have the what? Our displacement induced by the deformation, U over bar becomes, as we have said, W over bar. And what? R over bar, which is the position, becomes X over bar. Okay? And consistently, R0 over bar becomes X0 over bar. Okay? Let me just mark this equation, because now we can rewrite equation star operating this substitution. Okay? Let's do it. Okay? And so this becomes P, of course, stays P, because we always want to derive the position of a point within the element with respect to the inertial frame, because we are always dealing with the absolute nodal formulation. Huh? And also R. But this becomes A operating on what? X0 over bar plus W over bar A. Very well. And so, eventually, we get that W over bar is what? Is A, if you want, to the minus 1, of P minus R minus X0 over bar. Now we know that A is an orthogonal matrix, so this becomes transpose, which is much easier. But this is exactly what we needed to, to calculate the deformations. Okay, so let's estimate this. We have everything here, no? Why? So this is known. This is known. This one here, we have just derived it last time, if you remember. It's this one. We have recalled it at the very start. It's here. So we have everything. So let's calculate this. What is the amount of the displacement induced by the deformation within a rigid motion for the case of a 2D isoparametric rectangular element? This is what we're doing. Well, if you do this, we only have to remind that A, for the 2D case, is the super well-known rotation matrix. So let's build up this W. This one here becomes A transposed operating on P, minus R. So again, if we get back here, it's basically this one minus the first part, no? So let's write it. And we get x10 minus of theta minus the initial position with respect to the local to the element frame, no? So it's x10 over bar, x20 over bar. If you do this matrix multiplication, what you get is the vector 0. Would you have expected this? Yes, this is how it should have been. No? When you have a rigid motion, there is no deformation-induced displacement. because there is no deformation, basically. No? No deformation induced displacement. And therefore, the energy is 0, the strain energy. Okay. So this tells us what? That according to the principle that we have studied yesterday, so continuity and capability to represent a state of constant stress, this kind of element type is okay. It satisfies the convergence requirements for within this kind of formulation, okay, because we remember that we always make use of an element type within a formulation. Okay. So again, the 2D possesses all the requirements to guarantee convergence. So it's okay. Okay.
By formulation, do you mean particular positions in particular structures?
No. By formulation, I mean the type of description that you are trying to achieve for a given physical quantity. For example, as I was expressing in the previous lecture, we have the absolute nodal formulation, and we'll see today another formulation. Okay, so in the absolute nodal formulation, we want to describe all the quantities with respect to the inertial frame directly. That's why it's called absolute. Okay, so it's not a position of a structure. It's a methodology. It's an approach. Okay. Okay, and within that approach, you make use of different elements. As we have seen last lecture, we have the 2D element, we have the beam element, always within, so far, within the absolute nodal formulation. Okay, now let's try to do the same thing for the beam element type. No? So we verify verification of energetic consistency, if you want. So once again, what we do now is what we did already. So we will consider again a rigid motion. In this case, for the beam element. So I hope it's should be this one. Yeah. Okay. So you see again here we have the beam element, And we have all the element coordinates, the nodal coordinates aligned along the axis of the inertial frame. And we have and we suppose that the element undergoes a displacement, a rigid displacement r, and a rotation theta. Okay. Okay. Here and here. Okay. Again, let's calculate, as we did yesterday, the element coordinates. So first thing, with respect to, again, to the inertial frame. So we have, again, if you remember, we have 6 nodal coordinates. These are much easier. So these, in fact, we can actually derive one by one. So E1, how much is it? E1, the coordinate, the nodal coordinate E1. Make sure to have noted where the local frame of the element is. You see, it's not in the middle anymore; it's in the first node, the origin of the element frame. So E1, which is the position, again, of the node 1, in particular its component along x1, described with respect to the inertial frame. How much is it? If you look at this. Again, this is node 1. Huh? This is node 1. Is the component along x1 of the position vector of node 1. Say whatever. Very easy. Of course, the same goes for direction 2. What about the angle that at node 1 the element forms with respect to x1? It's theta. It's theta itself. Very well. Now, just a second, because I'm seeing here there is a mistake, maybe. Okay, no. So, just remember that here the length is L of the element. So what's again the coordinate of node 2 with respect to x1? Okay. And for small rotations? Okay, we are always in the hypothesis of small rotation. Yeah? Very nice. How about the vertical? R2 plus? Huh? They would not be physically consistent. Okay. And the last one, the orientation of the second node. Remember that it's a rigid motion, so it has to be the same. No? Okay. So this is very easy. Therefore, since we have that T is equal to psi, and psi we have it for the 1D element, we have derived it yesterday. this becomes, if you do a little bit of math, it's R1 plus X1, 0, and R2 plus X1, 0, theta. Okay. All right. Now, as we have done just a few minutes before for the 2D element, let's go and estimate the elastic energy associated to this motion. So we have derived the position, the expression of the position of each point within the element, and let's go again for the derivation of the strain energy. Okay. So let's the strain energy allora, sorry. We have, in this case, we can basically estimate the elastic energy as it follows. It's a beam element. It's a beam element associated to a Euler, 1D Euler model. So I would say this is the contribution of two different behaviors, as we have already seen, the axial deformation and the flexural deformation. So for the axial deformation, we have that E, which is the Young's modulus, times A, and these together, they form the axial rigidity of the beam. The derivation, sorry. Squared. This one inside the parentheses is the axial deformation. This would be epsilon xx. Yeah? What you call it, epsilon xx squared. Okay. Plus the axial, the transverse, the flexural deformation. And so here you go with the EI, flexural rigidity. Okay, and this is basically what you call the curvature within brackets. This one here is the square of the curvature. Okay, so these are things that you have seen even too many times. All of this being derived with respect to in here, okay, across the length. Please note that here we are doing an integration toward the length because here we have the areas, and here also we have the inertial properties. Okay, so physically we were correct. Again, non vanno bene? Certo. Okay. So at this point, what we can do is to basically resort to the same description of W, single element body. So resorting to the same single element body analogy. So as if we had a body with a single element, as we did before. W is A transposed P minus R minus X, 0. Okay. Now, remember that here now we are considering small deformation. So A, we have seen it before. Okay, so if we do the hypothesis of small and again, make no mistake, here we are talking about the rotation induced by the deformation. We are not talking about theta. Sorry, we are not talking about the rotation induced by the rigid motion. Okay, here we are talking about the rotation induced by the deformation. What we have is that we have to linearize this. And if we linearize this, what do we get? We have already seen it. But this has a problem. This matrix cannot be a rotation matrix. Why? Okay, it's not super evident to see like this, but if you do this and you, okay, let's try to do it actually. If you do A applied over A transposed, let's see what we get. 1 minus theta, theta 1 applied over 1 theta minus theta 1. Okay, so we have this times this, and we have 1 plus theta squared. Then we have this one times this, and it's 0. Okay. Then we have this times this, and it's 0. Okay. And then we have this one times this one, and we have 1 plus theta squared. Is this what we should have got? No. Huh? We have already introduced that. We have already introduced the hypothesis of small rotations, and that allowed us to get theta instead of sinus of theta and 1 instead of cosinus of theta. We cannot use it again. So this is not 1. Whatever theta is small is not 1. Okay? You cannot enforce it repeatedly as many times as you want. It doesn't work like this. Okay? So since this is this should be an identity matrix, in order to do that, we should do what? Divide these two quantities of the same factor. And so we pre-multiply this one by 1 over 1 plus theta squared, and this by 1 over 1 plus theta squared.
But it's the same assumption, isn't it? Theta is very
Mm-hmm. But here, no, because this is not a limit operation. We're not doing a limit operation here. When you say that this is not this, it's close to this, but it's not this. Well, it has to be this. Okay, so the approximation that we did was in the estimation of theta, of A, of the rotational matrix. But this is a mathematical property that the rotational matrix has to possess, otherwise it's wrong. Okay. So all of this to say that our rotation matrix is sorry. Now, if you multiply this by its transpose, you get the identity matrix as it should be. Therefore, if you calculate W, the vector, let's see what we get now. It's 1 over 1 plus theta squared, sorry, multiplying 1 minus theta, theta, and 1, applied over x10, x10 over bar theta, minus initial position, r, x0 is x10 and 0. Okay, so the local initial position of a point within our element is x10, and then since it's a 1D element, the transverse coordinate is 0. So first of all, this is not 0, because it actually amounts to x1 over bar multiplying 1 plus theta squared minus 1 and 0. Okay? So it's 0, second coordinate, and 1. So okay, let me rewrite it clearly. One plus theta squared minus 1. Okay. All right. Since we have W, now let's calculate the deformation that we have inside our energy definition, the strain energy. So we had all of this was done to estimate this one, and then U. Okay, so let's do it. So we have that okay. We just made the derivative. Oops. And therefore, this becomes and sadly, this is different from 0. So we have a problem here. This means that, and we will write it clearly, if you use a 1D element, beam element type, within the absolute nodal formulation, you get an energetic misrepresentation, because when you try to represent for small rotations, when you try to represent a rigid motion, you get a non-null value of the strain energy associated to this motion, and this is not possible. This is not right, and therefore you do not satisfy the necessary conditions to get convergence. So this is the start of a slippery slope. And let me stress out this final part. The 1D beam element type is not capable of represent correctly rigid body motion in the absolute nodal formulation. Because as you can imagine, 1D beam elements are used everywhere, every day. So how is it possible that now we prove them wrong? Because there are other formulations in which they work, and we will see how. We will demonstrate it now. Okay. In fact, these kind of elements, which are typically they are elements which are representative of a structure whose thickness direction has been integrated. Okay, so this is 1D element for a beam, or 2D element for a plate or for a shell. So the shell elements are just like that. Okay, they typically feature, so they are not 3D elements. They typically feature rotational coordinates. Okay, and they are very useful for the things that we have said yesterday. For example, to implement constraints, boundary condition easily. But they have this problem. So in order to make them usable, there are other approaches in which they work at the cost of certain assumptions that we see now. Okay, so we build another frame, that's the meaning of formulation, another frame within which we are using the same element type, and within this new frame, they will work. Let's see. Of course.
We choose the rotation matrix, we modify the rotation matrix by dividing it with 1/5, square root of 1/5.
Yeah, we normalized it, in fact.
Would it still be accurately representing the body in the inertial frame?
In the inertial frame?
Yeah, I mean, if I substitute this in E is equal to R cascade, let's say.
But this is actually what we were doing, yeah? We were exactly doing that. So we were using that rotation matrix, linearized, to represent the rotation, the small rotation within the inertial frame.
Yes. So would that still be accurate because we have normalized this? Would that change the formula?
But again, so the idea is not that we have normalized it for our convenience. We linearized the rotation matrix. And if you linearize it, it's not just that you can write 1 minus theta, theta, and 1. No, that's not the correct linearization. The correct linearization is the one that foresees the mathematical properties of a rotation matrix. A rotation matrix that pre-multiplied or post-multiplied by its transverse does not get the identity matrix is not a rotation matrix. So we didn't do it because we wanted to, but to get the right one. Okay, the right, yeah. That is exactly the linearized version of the rotation matrix. It's nothing else. Right? Okay. So, as we were just mentioning, we got now a new formulation, which is called floating frame formulation. Let's see. Let's see right now what we are talking about. So we again consider the 1D beam element. So energetic, verify energetic consistency for 1D beam element. So just the same that we were doing before, but now we change approach. Because the HP now is that nodal coordinates are expressed with respect to the element frame. One, two. So before we had this. Now we have this. Let's call it so. So we do not want anymore to relate the nodal coordinates expressed with respect to the inertial frame to the position of the point with respect to the inertial frame. But we want to relate the solution, the nodal coordinates expressed with respect to the local frame, so that's why there is an overbar over D, to the position of each element, of each point within the element, described with respect to the element frame again. And you should already wonder that this actually will have consequences, positive consequences for what we were looking at. So in this case, first we have to derive our psi, because before we already knew the shape matrix for the one D beam element, but now we are actually changing formulation. Okay, so we go again with a polynomial expansion. So let's, sorry. Let's derive the element shape function for 1D beam element in this new formulation. And again, what we do is to basically assume a polynomial expansion. The physics does not change, no? It's always a 1D Euler beam. So we can use the same exact expansion. So we have H0. But in this case, you see, it's not anymore P here. It's X over bar. Okay, it's not P as before. We do not want to express directly the position of a point within the element with respect to the inertial frame. We pass first through the element frame, and then we will see what happens. So we have here, again, a linear variation for the axial displacement, or the axial position. And the cubic one okay, again, why is it there? Because the model of the physics is the same, so 1D Euler beam.
Professore, si è bloccato il video.
Okay, just a second. Va bene?
Sì, grazie.
Okay, so again, we proceed as we know. Please note that in this case, our E, the nodal coordinates, they are not anymore oriented with respect to the inertial frame, but with respect to the local frame, you see? Okay, as we have said. Okay, so we proceed. Writing matrix form as typical. No, sorry. It's always the coefficient matrix. Okay. But again, this is the following. Just as we have done yesterday. But this is some slightly different thing, and we will see that it will have big impacts on the following formulation. Now, we impose equality at nodes, meaning that we have that x1 over bar at 0 must be exactly 1 over bar. Okay. So again, just to give you the frame, here we are deriving the interpolation that will be capable of expressing each position of a point within the element, knowing the position of the nodes. Okay, this is what we are doing with the interpolation. Okay, so of course, this interpolation, when we are exactly at the nodes, has to give the value of the nodes, the nodal coordinates. That's what we are imposing. Okay. So x2 has to be equal to E2. And then again, as we have done last time, we have x1 prime, so the derivative with respect to x1, 0, at 0, is E3. Okay, let's write it. Tangent of alpha at 0. And this is more or less in the linearization approach. Okay. Okay, we always are in the small rotation hypothesis. This is for node 1. For node 2 is, of course, the same. Again, before over bar over bar. Okay. Now we write the same thing again in matrix form. Just a second. To see if this is consistent with the other. Yeah. Yeah, yes, it is. So it's this, like so. And this is with the overbar, okay? Again. With this matrix, in this case, is the following. It's 1, 0, 0, 1, 0, 0. Okay. And as we have now learned to do, it's not P anymore, it's X. Okay. And this is again the shape matrix, the element shape matrix. And with no surprise, if you look it up, it basically says the same. It's basically the same that we have already defined. Let's write it here. The typical one. Why is it the same of the element the shape of the shape matrix, the element shape matrix that we have already defined in the other formulation? Because it's the same element type. The same element type. And what defines the element type is this one. It's the way you reconstruct of course, apart from the nodes, how many nodes, the way you reconstruct the field within the element, starting from the solution of the nodes. And of course, this information contains in itself the physics. Okay, so it makes sense that it is the same. What is not the same is how now we relate this to the inertial frame. Okay, can I proceed? Okay, yeah. Okay. Because now we now consider a rigid motion. Okay, again, okay, for this kind of element. It should be the same. Oops. So here we miss the theta. There's a mistake. Okay. So the same body, the same element 1D elemental, but this time again a rigid motion. Let's see how to describe it. So as you should have already learned, the first thing is to derive the nodal coordinates. But this time, the nodal coordinates are not anymore described with respect to the inertial frame. And this makes the big difference. So look at the position. Look at the position of the local frame, so of the element frame. So what is the component along I1? 0. E2? E3? No. Because it's the mutual orientation between the element and E1 this time. E4? Correct. E5? E6? Okay. Now, we do not have to anymore derive P, but we have to derive X over bar. And if you do it, this becomes like this. Okay. So this is the position. So at this point, we can again describe what we have before. So we have actually, yes, well, okay. Okay. But this one is exactly X over bar, no? Okay. In fact, all of it, in fact. Well, yes. because if you know again, the displacement, sorry, here it's like this, the displacement induced by the deformation is the difference between the actual position and the initial position. Makes sense, no? But this here we have it. We just derived it, which is x10, 0, minus the initial position, which is x10, 0, and this time it is 0. So, as you can see now, in this kind of approach, in this kind of formulation, the 1D beam element type is energetically consistent. So it can describe a rigid motion. And the cost, at a cost that we will see in the next lecture, again of small deformations. Now, to conclude this lecture, can you understand, can you tell me how we actually, what is the point in which we get these results? So how this magic works? Why do we get this in the overall formulation? Can you exactly detect at which passage mathematically? What is the reason? Why conceptually? Apart from all the demonstrations that we have done, why are you able to get that? What was the weak spot of the previous approach of the absolute nodal formulation for 1D beam element? Just think about it for some seconds. Kind of. The thing is that before, we directly had to relate nodal coordinates to the inertial frame. In so doing, we had to encompass large, possibly larger rotations, rigid rotation, within the element formulation. Instead, in this case, so the A, as we have seen, had to be linearized. Okay? In this case, instead, we always stay within the element frame. So we do not even see the rotation, the rigid rotation. And therefore, we do not introduce the approximation due to a linearization of such rotation. No matter what happens outside, I can go wherever in terms of rigid motion. I always focus on the element. So while before assuming a linearization of the rotation, okay, undergoing at the element nodes meant also to linearize both the part due to rotation, to deformation, alpha, both the part and the part due to rigid motion. I was not able to disentangle these two things, okay? So if I linearize the rotation at the nodes, if this rotation is due to deformation or is due to rigid motion, I cannot distinguish. In this case, instead, when I linearize the rotation, since I always stay within the element, over the element, I only linearize the part due to deformation. Okay, and that's why when I have no deformation, like in this case of rigid motion, I do not make any approximation, any mistake in terms of the expression of the strain energy. Okay. Okay. So this is all for today, and on Monday we will see how this new formulation, so the no floating frame formulation, basically is used to build a discretization of the overall body. Because again, okay, all of this is very nice, but with this formulation we relate the nodal coordinates to the local frame, but we still have to pass from the local frame to the element, from the element frame to the absolute formulation. Because eventually when we describe the physics, the dynamics of a body, we always have to go back there. So somehow we have to go back there. We will see how. next week. Stop here the recording.